Okay, the second class of force that we're going to be interested in thinking about are called surface forces. As you might imagine from the title, these are forces that are exerted on a face of our fluid element directly. So these come from direct contact with the surroundings. So that's maybe relatively obvious. But we have to bear in mind this complication that we mentioned last time, that our area, or our surface that we think about, has an orientation, and force has an orientation as well. And so we're going to have to think about both shear forces and normal contributions. And since we'll express them in force per area, they're really stresses that we're going to have to think about. So we're going to have to think about stress contributions, and we're going to represent them in terms of this tensor tau. So the most important part of this is to, first of all, recognize the sign convention that is used in trying to understand these. We have two free indices, I and j, and so we need to think about what those mean. And so the convention that we will use, and it is a convention, is that we're going to think about tau ij as going to be a force. It's acting on a surface. It's going to have a unit normal that is pointing in the I direction. And the force itself will be acting in the j direction. And so that's, you just have to write that down and commit that to memory and think about it. But we can think easily about some simple kind of examples. So if we think of a little material element, dv, in our control volume, then we can now start asking about forces. We already have worked out that the body force would be rho g dv. So we know that one, but now we can start thinking about forces that are acting on this. And so the first one that we might think about would be a force acting on this surface. So in this case, the normal vector is pointing in the 2 direction, and the force is pointing in the 1 direction. So this would be the contribution that we would call tau multiplied by the j component is the direction of the force, and so the j component is in the 1 direction. The normal is in this direction, so this would be tau 2, 1. Similarly, if we were to ask what is the contribution on this surface, then on this surface, now we would have a normal that is pointing in the 1 direction. So we would have that this would be tau with a 1. And the force itself is acting in the 2 direction. So this contribution would be tau 1, 2. Alternatively, we might think about a force that is acting in this direction. In this direction, if we're thinking in this direction, then now the direction we're pointing in is 2, and the unit normal is also aligned in this direction. So we would write this as tau 2, 2. And similarly, you might imagine that these forces in this direction are tau 1, 1. So with that, hopefully, we can understand the convention that we're going to use in the rest of this. And there's a number of important considerations that people will make about thinking about the forces acting on a material element. So if we consider all of these quantities by considering forces on a surface, on a material element, that's in equilibrium, we make 3 important conclusions. And so the first one is that if we have no non-conservative body forces, then if I do things like taking moments about this and think about all of the forces that are acting, things like the normal force per unit area and the body force all act through the center of mass of this little material element. It's these shear components or the ij components that don't. And if we think about this and we assume that this is in equilibrium, then we'll find that actually that the tensor, that the stress tensor is symmetric. And if we want to write that, we can write that in two different ways. We can say that tau is equal to its transpose. That's in Gibbs notation. If we want to write it in its component form, we would say that tau ij is equal to tau ji. So a proof of this would basically essentially write down the equations of motion for this and think about whether this material is accelerating. And you'll find that unless all of the stresses are symmetric like this, that the material element would continue to accelerate even if we weren't acting on it directly. And so that doesn't seem physically reasonable. So that's the first important thing. The second important observation is that for a fluid element in static equilibrium, we've already said in our introduction to this class that a fluid will respond in association to its shear stresses. So a material element will flow. If I take a glass of material, it'll flow, but eventually it'll come to rest at an equilibrium shape where there's a body force acting on it, and it can't support shear stresses. So in static equilibrium, all of the shear stress components are zero. Are all zero. And so the only forces that are acting on it are normal stresses. And so we might write that tau, it's symmetric, and all of its off-diagonal components are zero. So we'll have terms that look like that. And at equilibrium, we'll have tau 1, tau 2, and tau 3. So those are the only stresses that are acting on it. And more importantly, for a fluid, if I was to put a pressure transducer inside there, then the only thing that we would actually measure in here is the state of pressure in the fluid. And so for a material that's isotropic, then not only are these only diagonal stresses, but all of the diagonal stresses are the same. And so our final conclusion might be for 3, that for an isotropic fluid, isotropic meaning it's the same in every direction, then it says tau 1 must be equal to tau 2 is equal to tau 3. And this gives us a definition of a pressure. And so one way of thinking about that is to take the trace of this, and the trace of this will give us the sum of those quantities. And so for an isotropic fluid material in equilibrium, we can write that tau is equal to, and we'll say that we'll get just a value that we'll call pressure along the diagonal, with all other terms 0. And so those are the terms that we can measure. And by definition, we always use the sign convention that pressure is positive when pointing inwards. And so when I think about a material like this, we'll think about pressure as a normal force, but it's acting inwards where our outward-facing normal. We always say, I'm under a lot of pressure, or I'm under a compressive stress. We always kind of feel pressure as a positive quantity. And so if pressure is a positive scalar, and we are going to use our sign convention here, then we must have minus signs in here to indicate that the pressure is a scalar of magnitude p, but pointing inwards. And so we can write this in index form in terms of a scalar p, and a tensor, which is the unit tensor 111, which we'll call I. And this is actually a great way of finding a definition of the mechanical pressure, that we can, by comparing these two expressions, it's clear that the pressure is nothing but minus 1/3 the trace of tau. And we'll use that as we go on as a way of defining pressure in a mechanical sense.